What happens if you have multiple objectives? So for that scenario, let's take a look at the difference between constraints and objectives, right? Typical constraints are actual material property, performance properties such as should be conducting electrically, should be optically transparent, should have target values of mechanical properties, and then it should be processable by a specific preferred method. When dealing with objectives, and you're looking at, do you want to minimize mass, which is typical for aerospace? You want to reduce carbon footprint, which might be the case for cars, for instance. If you want to reduce energy consumption, for example, in refrigerators. If you want to make it small enough, so volume should be minimized. So, for instance, portable electronics, mobile phones. Cost, of course, should be minimized as much as possible while still meeting design requirements. So, you can't go for a lower cost without reducing the number of features in certain cases. So dealing with multiple objectives means you need trade-off methods so that you can simultaneously minimize mass and cost, for example, since that is like a routine case in structures. Let's look at many variants of that and solve problems, especially when we get to the next week. So what happens when you want to optimize two objectives? So in this particular class, we will only look at outlining what is the approach for being able to do that. We'll outline how we go about doing that. Right? Solution is such that a candidate should meet the constraints but not necessarily optimum of either objective. And then you begin to plot the solution. So for instance, you find different combinations of mass and cost overall, going from light to heavy and cheap to expensive. So dominated solution is one that's definitely not optimal. So somewhere along this, where you can either have something that is either less expensive and lighter. Okay, that's a dominated solution. So you have better alternatives. A non-dominated solution that is one where it's at least at any given time the best for one of the metrics, right? But maybe not both. For instance, for a given cost C, right, this is the lowest mass. There's nothing better than that in this region. Or for a given weight M, there are more expensive solutions, but there are no cheaper solutions, right? That's a non-dominated solution. Mainly if you go towards this whole surface represented over here, they all represent various non-dominated solutions. So a trade-off surface, which is also known as a Pareto front, offers the best compromise between M and C for any given C or for any given M, generated by this dashed line and represented by these highlighted points. One approach to dealing with the situation is say, okay, fine, we are going to have and set an upper limit on cost and arbitrarily decide that this is your optimal solution. But at that point, you're only establishing a constraint on C. You're not really optimizing, right? It's not really an objective anymore. A way to look for an objective is to define a penalty function Z, which consists of both C and M. And we want to minimize Z such that for all combinations of C and M, we end up having the lowest value of Z. Let's say that cost is somewhat proportional to mass in some manner, and that constant of proportionality is alpha. Okay, so we make a trade-off plot. Here, since we're plotting M on the x-axis, on the y-axis, and C on the x-axis, we can rearrange terms over here, and in this plot of M versus C, you basically have these terms where Z by alpha is the intercept and minus 1 over alpha is the slope. These are the so in this case it's a linear plot, and so what you end up having is for a bunch of lines with a slope of minus 1 over alpha as represented over here, you look at various lines with an intercept z that are running parallel, okay, same slope, and you select the minimum value of z. In this case, it will be a z1. Let us see how this is put into practice, because at that point you end up getting a solution that is optimized by minimizing the value of z. That is the meaning of the penalty function z. What is the meaning of z? So the meaning of z is easy to see. Right? You have the value of z represent a value of c and m that is the smallest. What is the meaning of the slope alpha, that exchange constant? Right? Here's an example of price plotted against mass for various bicycles. Okay, and so you have various different materials satisfying different design constraints, and you have all these different dots present over here. So alpha determines the location on this trade-off curve over here, this extreme curve over here, and reflects priorities. Let's call it price per kilo. So you see for a plain carbon steel, for instance, or thereabouts, the slope over here is about $20 a kilo. If instead you're going to work with a titanium alloy, the slope is about $200 a kilo for that same Z line. So the question you have to ask yourself is, are you willing to pay an extra $1980 to reduce 1 kilogram on the bike frame? Think about it. Would it be easier to ride a bike that is made out of steel, ride it around the block hundreds of times to be able to lose a kilogram of your body mass? Or would you prefer to be sailing around on a titanium bike and paying that much more? Matter of choice, right? And priorities and affordability. But that is the practical example of what the meaning of the exchange constant alpha is.